Good morning, dear students. You know the task today. We have to find the moment of inertia of a hollow sphere whose radius is given as a, whose mass is given as capital M. So the procedure is very simple. We have done so many cases. So first of all, we will divide this hollow sphere's section, so that our three-dimensional problem becomes two-dimensional problem. So, you know, hollow sphere is obtained by revolution of a semicircle. Semicircular arc of a given thickness will revolve about this axis, and that will make the hollow sphere. So, first of all, we will calculate the total mass of the hollow sphere. Total mass of the hollow sphere will be 2 pi. In place of r, what you have to do? To find the radius of this shell, you will drop a perpendicular from P. P and Q are very close to each other. This angle is delta theta. This angle is theta. Okay. So, the perpendicular distance in 3D, imagine Q is little bit here, so that the perpendicular drift from P as well as from Q will be Pn, and the length Pn is A sin theta. So, it is 2 pi r, that is for the area, 2 pi A sin theta d theta multiplied by the density will give you the mass. So, you can observe that when you solve this, you will get a d theta. Sorry, this is not simply theta, d theta, it is a d theta, because we are calculating the area. We are taking the slides. So, it is in two dimension. In two dimension, you calculate the area and then integrate to get the total mass. So, you can observe that theta varies from 0 to pi, because you can have number of slices like this. So, this integral is very simple, 2 pi a square and then 0 to pi sin theta. So, that becomes, what that becomes is known to you. So, the density will become as m divided by 4 pi a square. So, first thing you obtain the density, next you obtain the moment of inertia. Now, moment of inertia is simply the mass into perpendicular distance square. So, perpendicular, for mass you have these terms, and then for perpendicular distance square, you have a sin theta. So, a square sin square theta. So, that will give you this integral, and when you substitute the values, you will get 2/3 of ma square. So, this is the simple case. We found the moment of inertia of a hollow sphere about OX. Now what next? Next is to find the moment of inertia of a solid sphere. Now solid sphere consisted of number of hollow spheres placed close to each other. So, how the figure will look like? You will get number of hollow spheres, concentric hollow spheres. So, one such hollow sphere can look like this. So, at a distance x of width delta x, you can consider one such hollow sphere, isn't it? So, consider number of concentric hollow spheres making the solid sphere. So what happens? Start our procedure. The total mass of the solid sphere, how it will be? It will be obtained by integrating the volume, because it is a three-dimensional figure. So you have to consider volume. So what will be the volume? 4 pi x square dx within the limits 0 to a. Why? Because x varies from 0 to a multiplied by density. So it will give you 4 pi rho a cube divided by 3. So ultimately you are getting the density as 3m by 4 pi a cube. Isn't it? Now, after finding out the density, you try to find out the moment of inertia. Now, in this case, it is much simpler. Why? Because the integration is also very simple. One thing. Another thing is, we are making use of the result which we have done just now. That is, what is that result? Moment of inertia of a hollow sphere about an axis passing through its center and perpendicular to it. It is 2 by 3 ma square. Isn't it? So 2 by 3 and then integral of, for mass you have the same terms, 4 pi x square dx, m 2 by 3 m a square. Is that okay? 2 by 3 ma square. What is that? That is the result we have just found. That is the moment of inertia of a hollow sphere about an axis OX. So it will come out, the integration is from 0 to a. So it will come out as 8 by 3 and then pi and then rho. Now for rho I will put 3m divided by 4 pi a cube. This is for rho, and 4 pi 2 by 3. Okay. And after that, integral of x to the power 4 dx. So that will contribute a to the power 5 divided by 5. So let us see what happens. Pi cancels, 3 cancels, and 4 gives you 2. So this is 2 by 5, 2 by 5 m. What happens to a? Is square, because cube cancels. So this is the final result, moment of inertia of a solid sphere. Now, I want to give you a thought. Now, see what happens. You have done so many cases. Now, almost we have taken variety of cases. The cases of 1 dimension, cases of 2 dimension, cases of 3 dimension. Now, particularly in this case, you can observe that moment of inertia of a hollow sphere What is that? 2 by 3 ma square. A is the radius, m is the mass. Now, if you consider the same sphere but whose mass is m and radius is a and the same axis about OX. ठीक है? This is 2 by 5 ma square. Which is greater? 2 by 3 or 2 by 5? So, moment of inertia of a solid sphere is less than moment of inertia of a hollow sphere, isn't it? Same axis, same mass, same radius, but you can observe that moment of inertia is 2/5 solid sphere and for hollow sphere it is 2/3. Now why this difference? Can you tell me? And what is the impact of it on the whole rotational body's motion? Okay, think on it. Now, let me tell you why. Why? Because moment of inertia is defined as mass into perpendicular distance square, isn't it? So, when you consider the case of hollow sphere, what happens? Hollow sphere, the mass is on the periphery, not inside. Okay? So, this mass into this perpendicular distance square plus this mass into this perpendicular distance square, this mass into this perpendicular distance square. So, it will be greater. So, mass into perpendicular distance square is greater. Greater than what? The mass into perpendicular distance square in the case of solid sphere. Why? Because in solid sphere you have the matter distributed evenly. So, the same matter, of course the matter is same, whose mass is capital M, but it is distributed evenly. So, moment of inertia of this mass will be mass into this perpendicular distance square. Moment of inertia of this mass will be this mass into this perpendicular distance square. So, when you consider the summation, you can observe that this is not contributing as much as these particles which are on the circumference only, they are contributing. Because there the distance is great. Here the distance varies. Sometimes it is smaller, sometimes it is greater. So that is the difference. That is why you get the moment of inertia of a hollow sphere greater than moment of inertia of a solid sphere. I hope this may create some interest why we are learning moment of inertia. Why you are learning moment of inertia? Since you want to understand the rotational motion of the bodies, because in the universe you have always three-dimensional rotational bodies, not stationary, moving, rotating, not only translating but rotating as well. So I told you initially also the mass is very important inertia. For a greater mass you need more inertia, more force, isn't it? So that mass is replaced by moment of inertia in rotational motion. Now, can you tell me the result if you consider an egg? If it is raw, what will be its moment of inertia? If it is not raw, if it is solid, if it is boiled, then what will be its moment of inertia? And which one will spin well? Okay, so think over this practical problem. That's all for today. We'll continue next time.